Begin recording. Okay, so today is Wednesday and it's 9th week, and I sent an email out about I don't know, about stuff. So so we're going to cover PCA today, and then I'll have a kind of a follow-up on it on Friday. And I think that'll be it for like new content. And during 10th week, I think we'll just kind of take it easy. I might have a topic of choice that I probably won't put on the exam. We'll talk about the I guess the last test that you'll take, and then I don't know, we'll just we'll see what we do. So anyway, I'll get started on PCA here. So PCA stands for Principal Components Analysis, and and the idea here is so this is also an unsupervised learning method. We are not there's no values to predict. We're just looking for structure within kind of the x values, right? So we have the input matrix X, and that's it. And we're looking for structure in it. And the idea here is you've got probably a data set with a bunch of variables, a whole bunch of columns, okay? And the columns, the variables in their data set, they're possibly correlated. And what PCA, Principal Components Analysis, is going to do is it's going to transform those columns, that data, into uncorrelated variables. And often the case is to do dimension reduction. This is probably the primary use of PCA, is to get dimension reduction. And basically the idea is if you've got a bunch of variables that are correlated, you might be able to reduce the number of variables and still capture or convey the variation that exists in the data, right? So so here's just a kind of a silly example, is that you might have a data set on say like housing prices, okay? You might have like a housing data set, and it might have a whole bunch of variables like livable square footage, total square footage, number of bedrooms, number of bathrooms, the lot size, the pool, roof style, the heating system, garage, carport, number of parking spaces, the date it was built, the quality of the kitchen, the floor quality, roof quality, the location, the zip code, the local school rating. I guess I didn't fit everything. There's other things like the median price of the homes surrounding the house itself, and things like that. Okay, and so you might have, depending on the data set, you might have something like 20 variables or 30 variables or something like that. Right, and we might be able to simplify that, right? We might be able to reduce the number of variables, and we can probably group a lot of them together down to just having 3 variables, okay? One being kind of just the overall size of the house. So the square footage, number of bedrooms, number of bathrooms, all of those things will generally be related to each other, right? If the square footage goes up, you can expect the number of bedrooms and the number of bathrooms also to go up, and things like that, right? You're not going to find a 5,000 square foot house with only one bathroom, right? And likewise, you're not going to find, you know, a 600 square foot kind of apartment or something with 2 I'd say, you know, three bathrooms or something like that. So I guess you can have like 1.5 bathrooms or something. So those things are going to be correlated together. And then another thing will just kind of be the quality of the house itself, and whether it has amenities, things like, you know, is the kitchen nice? Is the floor nice? Is the roof, you know, has it been redone recently, and things like that. Okay, and then the last will be kind of a rating of the neighborhood. Is it in a nice area? Are there parks nearby? Is the schools nearby nice, and things like that? The crime level and things like that. And I would say, you know, that kind of breaks down describing a home altogether, right? And you can kind of reduce just you know, if you want more details, sure, you can drill down into any one of these variables. But overall, if you just kind of want to get an overall feel for the house, you might be able to just get away with it, get away with just having 3 variables, and still capture a lot about a lot of information about the house. Okay, so so other aspects or other applications of dimension reduction. Here are some of these other things, and the idea behind it. You know, why would we want to reduce the dimensions? Well, it's just easier for our brains to think about if you only have a couple variables to keep track of, right? So so you know, I don't know if you've ever played like a role-playing game or something where you're building a character and there's all these different aspects, and and if you have too many different um, um, stats to keep track of, it can be hard, right? So dimension reduction is useful in that it kind of just boils things down to just 1 or 2 variables that are a lot easier to keep track of, right? So things like your GPA, okay? The GPA, you know, dimension reduction is useful for making comparisons, but it's very reductive, right? Just by definition, it is reductive, right? So the idea of reducing an entire academic career down to a single number is what kind of fuels the GPA, and you know, for better or worse, probably for worse, you know, that's what happens, and so you get these weird kind of artifacts of people trying to gain their GPA and stuff, but it's useful to it can be useful to just have a single number that represents someone's school performance, right? Similarly, like the SAT or the GRE will take something complex like intelligence, measuring someone's intelligence, and that's going to get reduced down to maybe 2, maybe 3 numbers, you know, like a verbal score, a math score, maybe a writing score. And not that that's a good metric, and it certainly, you know, doesn't take into account everything else, but it can be useful as some kind of measure of I don't know. I don't know what the right word is, academic performance or something, just test taking abilities and things like that, right? It is useful to have some kind of simplified metric rather than trying to look at everything all at once, right? Similarly, you know, your financial trustworthiness is reduced to a single number. This is known as your credit score, okay? And there's usually all kinds of different, all sorts of different factors play into the credit score. But once you have your credit score, then banks will often just use your credit score and how much money you make to decide whether or not to give you a loan, and things like that, right? This also happens in sports. So in the NFL, if you know, the quarterback will get a rating at the end of the game, right? It's going to take into account a whole bunch of stuff like the number of pass attempts, the pass completions, how many yards, things, number of touchdowns and number of interceptions, which would be a bad thing. And it takes all of that down, and it reduces something complicated like how well did the quarterback perform considering all of these different factors. It reduces it just to a single number, and you can compare kind of one quarterback with another by just comparing their passer rating, even if they have completely different play styles, right? Like you might have one quarterback who tends to take the ball and run with it in different situations and is quick on their feet, and then you have another one that greatly relies on just throwing and passing and stuff like that, and it'll take well, I guess the passer rating is mostly about passing, but it will take into account kind of different play styles, right? Someone who throws long passes versus short passes and stuff. Okay. Sporting events like track and field, also you can have so you might have something like the heptathlon or the decathlon, where athletes are competing in several events, and what you need is a way to rank them, because the heptathlon or decathlon, whatever event it is, there's only going to be one gold medal, silver medal, and bronze medal, right? So you know, somebody who does really well on the say 400 400 meter race versus someone who does well on the shot put or something like that, you need a way to kind of combine these scores, right? And so we're trying to reduce from 7 individual scores down to 1 score in the Olympic heptathlon. So it's useful. It's useful to reduce dimensions. And also just for the sake of reducing the number of dimensions for, let's say you wanted to only store, store fewer variables. It's also useful in that regard as well. So I want to give you a kind of a visual representation of this, right? So you can have an object in 3 dimensions, and if you shine a light on the object, it will cast a shadow, right? And the shadow is a 2-dimensional projection of the object, right? So we are projecting from a higher dimensional 3-dimensional space, and when it casts the shadow, it's a 2-dimensional projection, right? And depending on how we project, how that shadow is projected, the shadow might resemble the original object, or it might not. Okay, so let me see if I can do this. So here's a piece of paper, and then here is my hand. Okay, let's see. Okay, so here, if I do this, you can see kind of the shadow, and the shadow looks like a hand. I know my hand is blocking. The shadow here, right? But if I turn my hand like this, okay, the shadow that's being cast doesn't quite resemble a hand, right? It could be anything at this point. When you project it this way, it looks like a hand. When you project it this way or this way, it's hard to tell exactly what object this is, right? If you only see that shadow, it's hard to tell what it is. If you see this, if you see that shadow, you can definitely tell that it's a hand. And so similarly, when we do dimension reduction with PCA, what we want to do is we want a lower dimensional representation or lower dimensional projection of our data that resembles the original data. Okay, that's kind of the idea that we want to go for here. Okay, so here's let me explain. All right. So here is this website. It's called satosa.io, kind of based on the iris data set here. And it does, and it has this nice explanation of principal components analysis, okay? And so the idea here is that here's a two-dimensional data set, data that exists in 2 dimensions, and we can see in the X, the values vary, say, from like 2 to 8 point something, and then in Y it varies from, you know, around 3 to 7 and things like that, right? And we can see that X and Y are highly correlated, and thus we can effectively reduce this 2-dimensional data into 1 dimension, right? We can just line up the points in 1 dimension like this, right? And so what PCA will do is it tries to find a rotation or projection of the data that we're basically, you can also think of it as putting a light source over here, and it casts a shadow onto onto a line over here, right? And where does those shadows land? It's going to look like this, okay? You know, if there's 2 variables in the original data set, the PCA, the full principal components analysis, will also end up having 2 principal components. If you have 10 dimensions in the original data, then the full principal components will also have 10 principal components. You're going to have 10 things, but the idea is, you know, just the first few principal components will capture a lot of the kind of the variance and structure in the original data set. Okay, here's an example with kind of 3-dimensional data, and you can kind of get a sense of what the data looks like in 3D, right? And the idea is, so the way it's currently plotted, okay, if you look at just, if you just look at 2 variables at a time, so if you look at the X variable, this is what the, how the data looks like. If you only look at, I think right now, I don't know which one it is. I think X is probably this red dimension. If you look at just the blue dimension by itself, it's going to look like this, or the green dimension is going to look something like this. But then if you do the PCA, basically what we're going to do is we're going to try to find a projection of the data so that the, so this is how the data looks like in X, Y, and Z. But what we want is we want this first principal component to kind of maximize the variation that we see, right? And so when I run PCA, this is a rotation, right? So all we're doing is we're just rotating the data around, okay? And this is a rotation of the data so that kind of the projection here reveals quite a bit of the structure, right? So when you look at this 3D data, we can see there's 3 clusters here, 3 clusters in there, but it's difficult to detect all 3 clusters in the original X, Y, and Z dimensions, right? And so what we're doing is we're trying to find a rotation, okay, which kind of projects the data down into some kind of dimension. And so the first principal component will be a rotation so that the basically the shadow that this data set casts resembles the original data as much as possible, right? So the original data has 3 clusters, and this shadow kind of shows that it has indeed 3 clusters. Whereas these ones, we might get a sense that maybe there is some clusters that exist, but in the original X, Y, and Z data, it's difficult to kind of to detect that structure. But by casting, finding the light source to cast the shadow, we can see this here. Let me see. Something happened with. Yeah. So how do we do this, right? So yeah, can it be generated by setting different weights on each variable? And the answer is yes. So So this was just kind of a visual representation of the of what's happening here. And let me just show you kind of the math behind it, right? So we want to find a projection or a way to kind of cast a shadow of the data that resembles the original data. All right, so so we're saying, so mathematically, when we say we want a lower dimensional projection that resembles the original data, what we're saying is that we want a projection that captures as much of the variance that exists in the original high dimensional data, right? So in the original high dimensional data, there's variance that exists, and we want a lower dimensional projection that still captures a lot of that variance, right? And so if we if we're going to reduce the dimensionality, you know, you're going to lose some information, right? So when you go from 3D down to 2D or one dimensional, you're going to lose some information, right? But ideally, the information you lose is minimal, right? So here's kind of a 2D shadow of the 3D data, right? And here we feel like we're not losing a ton of information because there's not the third dimension that we're missing is not there's not a whole lot of detail, right? It's fairly flat, okay? Whereas, you know, when you project your hand like this, okay, the third dimension, there's a depth dimension, but we're not losing a whole lot by omitting it, right? On the other hand, if you project it like this, by losing this third dimension, you're losing a lot of information, right? So you kind of want a representation where you're capturing a lot of the variance, and the kind of the dimensions that you're throwing away don't have a whole lot of variance, right? There's not a whole lot of variance in this dimension of my hand. There's a lot more in this direction. Okay, so what we want is we're going to search for a lower dimensional projection that maximizes the variance in the resulting projected space. Okay, so so mathematically, this is gonna what it's gonna look like. Okay, so we're gonna say the original data exists in m dimensions. Okay, and the nth observation in the original data is going to be y sub n. Okay, which is basically a vector of length n, and so that's going to be y sub n1, y sub n2, all the way up to y sub nm. Okay, so you can imagine this column of y values for the nth observation. Okay, and then we want to project that data down to d dimensions, where d is a smaller number than m. Okay, and so after projecting this nth observation down to d dimensions, you're going to have x sub n. Okay, x sub n is another vector, but this time it's only of length d. Okay, and so what PCA will do is it's going to define d vectors. Okay, and each vector is wd, and wd is m dimensional, right? So PCA will kind of define this d by m matrix here, okay, or m by d, okay, and basically, when we say let's look at one of these components in X, okay, so if you look at this, it's going to be, so if you want to look at the first component, it's going to be basically the first W vector, okay, multiplied by y sub n, right? So W, we've got d of these W vectors, right? We're going to just, let's say we just want the first value, right? So X consists of d of these values. We only just want the first one. It's going to be just the first W vector, W sub 1, kind of dot product, or you know, W sub 1 transpose times y sub n. And basically, that first value, x sub n1, or any of these values, x sub nd, is a linear combination of the values in y sub n, right? And each of the values in y sub n are weighted. We're just finding different weights. We're finding a different combination of weights in W sub d, right? So if you're taking just one of these things, like if y exists, basically what we're doing is, you know, our original data, maybe it exists in 3 dimensions, and we want to project it down to, say, 2 dimensions, okay? So what are we basically doing? We're going to say, you know, let's use X at, 40%, Y at 50%, and Z at 10% or something like that, okay? We're just taking weights of X, Y, and Z. They don't actually have to add up to 1 in the way that I did. It's actually the norm has to be 1. So, but basically you're gonna put a weight on X, put a weight on Y, and put a weight on Z, and that's gonna kind of form your first principal component. And then you're gonna find another weight vector that puts another weight on X, Y, and Z, and that's gonna give you your second principal component. So you're gonna get, so if we wanted to go from 3 dimensions down to 2 dimensions, we would need to define 2 W vectors, and each W vector is going to be length 3. That's going to say this is how you combine your original 3 dimensions, and you're going to get a resulting 2 values here. Okay, and so so how do we choose these WDs, right? So PCA is going to choose the WD so that the variance in the projected space, so after we project it down, we want the variance here to be maximized, right? If we go from 3 dimensions down to 1 dimension, this is going to have the maximum variance, right? Whereas these ones will have less variance, right? So we want the projection that has the most amount of variance. Okay, so the first vector W1 will be the set of weights of the variance and the projected values of X, and the kind of the first elements of X are as high as possible. Okay, and then the second vector will also maximize the variance in the second component, but here's the requirement in principal components is that the second vector W2 has to be orthogonal to W1. Orthogonal is kind of like perpendicular, right? Perpendicular, but in a higher dimensional space. So so when you do W1 dotted with W2, you're going to get 0, right? And then the third vector has to be orthogonal to the previous vectors, and it's also going to maximize the variance in there. And so so basically, principal components you got here here's a set of 3 dimensions, 3 vectors, and they are all orthogonal to each other. You're never going to have, so if you have kind of your three vectors, they're always going to be orthogonal. You're never going to have something where the vectors are pointing in the same direction. They're always going to be orthogonal. Okay, and because only the directions are important, to avoid to have infinitely many solutions, we're going to just say the W vector has to be of length 1. Okay. All right. So so I'm going to walk us through a little bit of the math behind how are we going to find these W vectors, right? So let's just focus on the first W vector, right? So we're going to find the vector W1 so that the variance in the resulting X in the resulting projection is maximized, right? Okay, and so to make our life easier, what we're going to do is we're going to take the original data and we're going to center it, okay? So we can just subtract the column mean from each column, okay? And when you do that, your vector, y bar, is going to be 0 everywhere, okay? So we're going to just kind of make sure that the mean of the y's are all equal to 0. Okay, and we're just going to use, and to kind of keep everything easier, we're just going to use one weight vector, okay, one weight vector W, so because we're just projecting down to 1 dimension, and so rather than having to have subscripts for each of the different things, we're just going to have one weight vector W, and that's going to take each observation in Y, which maybe exists in, multiple dimensions. So here we have data that exists in 3 dimensions, and we just want to project it down to just 1. Okay, so how do we figure out what combination to use for this first principal component? Okay, so each observation in Y will be projected down to 1 scalar value, and we're going to do that by taking the weights and multiplying it, or taking the dot product with Y. Okay, so we're going to do W transpose Y sub n will give us the value X sub n, right? And then You do it for every observation in y. Okay. And so, what is the variance of this data, right? So sigma squared of x. Okay, we're basically just doing xn minus x bar, quantity squared, sum from 1 to n. And here I'm going to just use 1 over n, kind of the population variance, of the data. So this is what we have, basically the average squared distance from the mean. Okay, and if we recall that x bar, okay, so what I can do is I can show that x bar is going to equal 0 because, so here's x, which is w transpose y sub n, right? So x bar is going to be, take w transpose y sub n. This is a scalar value, right? If we add them up and divide by n, okay, that's going to give us x bar. And if we keep in mind that y bar, okay, which is 1 over n sum of the y's, if that's equal to 0, okay, then x bar is going to equal 0, right? So I can pull out the w transpose. I've got w transpose times this thing. This thing is y bar is 0, and so x bar is 0. Okay, and that's going to be helpful for us because, so our variance, okay, which is basically the sum of xn minus x bar squared, is basically going to just reduce to xn minus 0 squared, so xn squared. Xn itself is w transpose y sub n, okay? And so my variance is 1 over n times the sum of w transpose y sub n, okay? And maybe I should have put subscripts on all of these things, right? So w is, so y sub n is m by 1, and w transpose will be 1 by m. So this is 1 by m times an m by 1. So this is a 1 by 1 scalar value, right? And if we square this, okay, where you have a scalar value and we square it, we're also going to get a scalar value of 1 by 1, okay? And so the multiplication of this is going to be w transpose y transpose w, okay? So w is 1 by m, y is m by 1. For the dimensions to line, we have to multiply by y, which is 1 by m, and w m by 1, okay? So this is going to work out, all right? This is going to result in a 1 by 1 scalar value, all right? And so all I'm doing is taking this and I'm just expanding it out. And I can, so w is not affected by n, so I can kind of pull that out of the summation. So I have this thing, right? I got w transpose 1 over n, this sum of yn transpose w. Okay. All right. And so what is this? Okay. This thing. So yn, so what is y? Y sub n is an m by 1, and yn transpose is going to be 1 by m. So this is going to be an m by m matrix, right? So this thing is an m by m matrix, and what does it represent? Okay. Well, it's the covariance matrix, okay? So if this is kind of the definition of the covariance matrix, right? Here's the covariance matrix, and if we remember that y bar is equal to 0, then the covariance matrix is equal to this, right? This is an m by m covariance matrix, and that's exactly what we have here, right? So this is where we left off, and that's what we have. And we can say, oh, this is just a covariance matrix C, right? So now my variance is, my variance sigma squared of x is W transpose covariance matrix W. All right, is this okay with everybody? So far, so good? Okay, and again, this is all because we centered our data first, right? This we've made our life a lot easier by centering the data. Okay, so I've got our variance to be, so now I have an expression for the variance of x after we've projected the data, and it's basically our weight vector w, okay, multiplied by the covariance matrix times w. Okay, so what we want to do is we want to maximize the variance, right? So here's our variance, W transpose covariance matrix times W, right? So we've got W. This is the, we want to maximize this, right? And, you know, we have to keep the constraint that W transpose W is equal to 1, right? Otherwise, I can just pick infinitely large W, and that's going to maximize this. But we don't want that, right? So we want to maximize this variance subject to the constraint that the length of W, that is W transpose W, is equal to 1, right? So this is just kind of an arbitrary value that we've chosen, but we're going to say that this length has to be 1. Okay, so if you want to maximize subject to a constraint, we're going to use a Lagrange multiplier. So, so we've got, you know, Lagrange multipliers. This is we did it earlier with support vector machines, although we got into this quadratic programming situation and we got stuck. But now we have it for this, and so we've got the variance, and then we're going to subtract off lambda times basically the constraint, which is W transpose W minus 1. This thing is basically 0, right? And we're going to take the derivative of this thing, and we're going to set it equal to 0, right? So the derivative, whatever this is, W transpose CW, right, with respect to the vector W. So if we recall all the way back to kind of like our very first lecture, that wasn't a pep talk. This is going to be 2 CW, okay? And then lambda W transpose W with respect to W will be 2 lambda W. And then this is going to be plus a lambda 1, but with respect to W, that zeroes out, right? So this is what we have. We got 2 CW minus 2 lambda W is equal to 0. And solving, well, we haven't solved for W yet. Basically, I got the covariance matrix times W is equal to some constant value lambda times W, right? And what do we need now? We need to solve, what we want to do is we want to solve for W. All right, okay, so how do we solve this, right? We got a matrix times a vector is equal to a scalar times a vector. Is there, is there a name for this? Matrix times a vector is equal to scalar times a vector. Yeah, there we go. Okay, the eigenvalue and the eigenvectors, right? So you've got a matrix times a vector is equal to a scalar times a vector, right? And so the solution to that kind of setup is that W is an eigenvector of the matrix C, and lambda is an eigenvalue of the matrix C, right? So you find the eigenvector eigenvalues of the matrix, and I didn't put any notes on this, but you should have learned this in your linear algebra class, right? And so the idea is, if you think of every matrix as some kind of transformation, right? So if you think of, if you have like a 2x2 matrix, basically you're doing some kind of linear transformation to kind of the coordinate plane, right? So you're either like skewing it or rotating it or scaling it, you know. You're doing, like, say if you've got your kind of coordinate plane, you can do all sorts of stuff to the thing. And an eigenvector is basically a vector. So you have a certain, like you have an arrow in this eigen, like an arrow that exists on the the coordinate plane that even after the transformation, it points in the same direction, right? So as long as the arrow points in the same direction after the transformation, then that we would consider that to be an eigenvector. I think at the very beginning of the quarter, I linked to a YouTube playlist, 3 blue, 1 brown, linear algebra, right? And so you can think of, so watch this video on linear transformations, on how basically matrices are linear transformations of the kind of the coordinate plane, and then watch the video on eigenvectors and eigenvalues. You know, or maybe you remembered everything from linear algebra, you just took 115A, and so this is all fresh in your mind, so you're all good. But if you feel like, oh man, I don't remember what this eigenvector, eigenvalue stuff is, I strongly recommend just watch this video, number 3, and this video, number 14, okay? Number 4 is also great. All of these videos are great, really, really. You should watch them all, but you know, it's a couple hours, right? But but anyway, watch the linear transformations video, and then watch the eigenvectors, eigenvalues video. That's still a good half an hour, 20-something minutes of your time. Okay, so anyway, the W that will maximize the variance, right? Remember, let's not lose sight of what we're trying to do. Is we're trying to maximize the variance of the projected data. The W that's going to be doing that is going to be the eigenvectors and eigenvalues of the covariance matrix C, right? So the eigenvalue eigenvector pair with the highest eigenvalue will be the projection with the highest variance, okay? And that's going to be our W1. If you have multiple of these things, the second highest eigenvalue will correspond to W2, and so on until, so if you have, if C is M by M, you're going to have M of these eigenvector, eigenvalues, right? And so just kind of to summarize, what we're going to do is to go from M dimensions down to D dimensions. First, center all of our data, so everything has a column mean of 0. In the homework assignment, I kind of have you walk through all of this. There's an optional step. You can choose to scale the data. If you scale the data, then what is it, right? The covariance matrix of scaled data is equal to the what matrix? It would be the correlation matrix, right? So if you scale the data, it'll be also the correlation matrix. So anyway, so you find the covariance matrix C or the correlation matrix C if you've scaled the data. And then you're going to find the eigenvalue eigenvector pairs of that matrix, okay? And then if you want to reduce down to D dimensions, just select the D highest eigenvalues and their corresponding eigenvectors, right? And then the resulting X is going to basically be Y times W, right? So W, each one is M, but you've only selected D of them. So W is M times D, M by D. And so you do Y, which is N by M, multiply that by W, which is M by D. And the result is X is going to be N by D, right? So you're going to still have N observations, but now only in D dimensions. And that's what we're going to do, okay? So, so on Friday, I'll just do a few examples of this kind of stuff. Today, we kind of just walked through a little bit of the math behind it and the setup, and that's what we've got. 115A is so painful, I will never forget. Yeah, well, proofs are hard. Proofs are hard. I struggled a lot with proofs, so I feel you. So yeah, so anyway, I enjoy math to a degree, but yeah, proving things, yeah, no. Oh, quiz answer is good. Yeah, quiz answers. Today is 9th Wednesday. It's D and C. So dog for the first answer and cat for the second answer. So D and C for the quiz answers. Okay, and that's it for today. We'll see you guys on Friday. We'll play around with this, right? Yeah, I'll get rid of the quizzes in week 10. Yeah, so I had set them up, but week 10 will be optional attendance. So we'll see who the true. I'm just kidding. So maybe we'll see you week 10. Maybe not. It doesn't matter. No quizzes week 10, and we'll see you then. Okay. See you Friday.